Welcome to Physics 2425, Lecture 16 on sound. So in this lesson, we're going to continue our discussion of waves, this time going back to kind of the basics of sound, which is a longitudinal wave. And we're going to explore different aspects of sound. We're not going to cover absolutely everything that we could talk about. There's some topics that are really interesting, but are not strictly covered in this course. So I do have some links to some of that later on. But if this is a topic that really interests you, it does me. I'm a musician. I play lots of different instruments. I like to sing. And so this particular topic just excites me. And I wish that we could do lots more demonstrations. So I'm going to try and include as much of that as I can here within the limited range of this video. So looking at sound waves, sound is a longitudinal wave. When we talk about longitudinal waves, those are waves in which the propagation of the medium, so in this case, these particles here are moving in the same direction that energy is transported. So we can see that our particles are moving back and forth. They are moving parallel to the direction at which that wave is being transported. Now, what we hear as sound is dependent on our ears. So what you're hearing right now is the fact that my larynx has vibrated in my throat and has created a pressure difference, and then that wave transmits through the medium and propagates and vibrates and collides. Those air molecules are colliding with all of the air molecules around them, and they're transmitting that collision and that pressure wave further out. And they're going into my microphone, which is then getting stored as an electrical impulse, which then comes out of your speaker and creates a vibration out of your speaker. And then that vibration hits your eardrum. Your eardrum then vibrates, and then your brain translates that electrical signal into sound. And that's what you are interpreting as sound. So the average human can hear sound waves between around 20 hertz and 20,000 hertz. But you can have subsonic and ultrasonic sounds, so that are outside of human hearing. So there's animals that can hear sounds that are lower than we can hear. And of course, there are animals that, like bats, that can hear ultrasonic sounds. So we're going to just kind of see what these frequencies for the range of human hearing kind of sound like. So I do want to warn you right now that you might need to adjust the volume on your speakers. So I'm going to start off with a low frequency sound. So right now it is actually playing a sound. That sound is 3 hertz, and 3 hertz is theoretically below the threshold of any human hearing, so you shouldn't really hear anything right now. One thing I will say is that lower frequency sounds are often softer, they're lower amplitude, they carry less energy. The higher frequency sounds tend to be louder, so as I increase the frequency, I'm going to start with the volume up a little bit higher on the tone generator, and I'll have to turn it down. But I'm going to keep it loud at the start. You may not hear a sound, but sometimes you can feel a sound. I don't know if you've ever kind of felt a sound, kind of like the fingers on the chalkboard type thing. You can sometimes feel those vibrations like in your bones. That you can't necessarily hear with your ears, because cartilage in your ears versus the bones, different densities are going to have different abilities to kind of transmit the sound waves. So I know I don't have very good low range of hearing, so it's going to take a while before we get to a frequency that I can hear. That's a problem that I know I've had, not just because I'm old. So play along with me here for a sec, and let's see, when do you hear a sound? So playing a sound here. So this is 20 hertz. If you have really good hearing, you may be able to hear it. Got to be careful because I can hear the fan going in my laptop, so that might be interfering a little bit. 50 hertz. Now I can hear that. That is 109 hertz. I'm hearing a very low thrum that is different from the fan on my computer, but I'm not sure if you can hear that yet. So here about 140 hertz, you're probably starting to hear something. And then we're going to just kind of increase incrementally so you can kind of hear how those frequencies change. I'm going to start decreasing the sound a little bit. Here's where it starts going a little quieter again. So we're at about 12,000 hertz. 20,000 is around the max for human hearing. Gotten really quiet for me. And it's here at 18,000. I can't hear that. I can't hear that at all. But maybe you can. I'm not sure. I can hear that. 15,000. But I can't hear 18,000. So one thing I do suggest you do is maybe click the link and play around with it and see what is your range of hearing. What can you hear? When you have the ability to control your own volume levels, what can you hear? What is your range of hearing? Maybe you need a hearing aid. Maybe I'm feeling like I need one right now too. All right, so going back kind of here to kind of this wave. So with this is a pressure wave that is being created in air. So there's an air pressure being transmitted. It still has a sinusoidal pattern, but this wave is not propagating in like the Y and the X direction like this. The wave itself is just propagating just in our X direction. The particle motion is just in the X direction. So this is a little bit different than some of the waves that we saw before, where we had like a rope wave, the wave on a string, where the string itself was moving up and down. That was that's our transverse wave, but the energy was propagating sideways. So this is the energy and the wave are all transmitting parallel to each other. So if we take a look at our wave equation, so we have seen this wave equation before, but this, in this case, is going to be very, very similar. There's just a little bit differences when we're working here with a longitudinal wave. So the first thing, what we're defining here is Y is a little bit different. So when we are looking at this equation, Y is actually going to be a horizontal position. So if I define this position to be kind of like X equals 0, when my Y value is positive, that means I've had a displacement that is to the right. And when my Y values are negative, that means I've had a displacement to the left. So my wave is varying with a horizontal position X and a position time. So this is one snapshot that is showing lots of different X values. So this is a Y versus X. But in this case, my Y value is not a vertical position. It is actually a horizontal position. So I can see that this point right here that I have drawn here, there's been no displacement. That particle right there is actually where it's been. It's representing kind of the center of this oscillation. The next point where that is here. Now, these particles over here, kind of on this side, they're closer together. So they have been moved and shifted to the left. So they've been shifted to the left. So that way we are going to have negative Y values. So in the range from here to here, all of these particles have been shifted to the left. So we are getting kind of those negative Y values over on this side. And even as I go past that here, I can see that I'm still shifted to the left. So I still have negative Y values. It's just what's happening here is they're not getting shifted as much. So you're getting a smaller amplitude shift the closer you get back to that central point. But all the particles over there are shifted to the left. Now, because we're closer and we're more compressed over here, that means that these particles over on this side have been shifted right. So in this section, we're getting positive values for Y because we have had a shift to the right. So that's kind of how you would read this. Now, we could look at this as a snapshot in time. And what you would do instead, if you were looking at a snapshot in time, is you would pick like one location. And I would pick this one location right here. And then I would see how does that pressure wave change over time as it passes through that one instant. It will still be sinusoidal, okay? So we can have that displacement in terms of position or time. This one in particular is a snapshot in time. Now, this version, like of this equation, I don't use very often. It doesn't make as much physical sense as to me. Now, the other version of this equation is actually in terms of pressure. And it looks really, really similar. So we're still looking at this sinusoidal wave. It's still kx minus omega t. And as a reminder, k is our wave number. Our wave number is 2 pi over our wavelength. And then we've got omega, which is our angular frequency. Our angular frequency is 2 pi f. Our wave number is 2 pi over wavelength. So all of that is the same as when we looked at previous waves. Now this is a pressure wave. Now they're using a lowercase p for pressure because they're going to use a capital P for power. So we're using a lowercase p for pressure here. So this is still a wave that can vary in terms of horizontal position in time. But now we're not looking at the actual motion of the particles. We're looking at pressure. So if I was to stick like a pressure gauge here, and I was to measure the air pressure at that point, that's what this graph is now showing. So the middle line here would essentially be our atmospheric pressure, the baseline pressure. So if there was no sound wave, there was no pressure wave occurring, that is the center of the wave. So areas of high pressure are positive and areas of our lower pressure, lower than the atmospheric pressure. So when we describe pressure, we can describe the structure of this longitudinal wave. We use the term rarefaction. Rarefaction is going to be when we have low pressure. That's when there is more space between the particles than there would be in the standard air at atmospheric pressure. And then we would have a compression. Our compression points are going to be where our particles are close together. So these minimums here are going to be the rarefactions, and our compressions are going to be the maximums here. Now, what the magnitude of that maximum is this BKA. And I'm going to tell you this version of the equation is not on your formula sheet. This is not something you have to have memorized. It may show up in a calculation on the homework just out of kind of curiosity. But this capital B is the bulk modulus. It is basically a measure of kind of the density and some of the elastic properties of a material. And it's going to be a constant, so it's something that would be experimentally determined for every material. And then we got our wave number here and our displacement amplitude. So the amplitude of that displacement, so the bigger the amplitude of the displacement, that would have been from the previous example, looking at the amplitude of that wave, how far the particles are displaced horizontally at their maximum is going to be the displacement. So basically, those are the kind of properties that are going to determine the pressure wave. So we've got our wavelength here as part of the wave number. So we can see that if we have a larger wavelength, that wavelength's in the denominator of the wave number, so we're going to get smaller pressure. If we have a bigger amplitude wave, we're going to get more pressure. If we have basically more density, because the bulk mod just has a lot to do with density, we're going to have kind of higher pressure waves as we go through. Now, the speed of sound, is different in different mediums. So when we look about air at 0 degrees Celsius, which is of course freezing, is about 331 meters per second. Air at 25 degrees Celsius, which is warmer than room temperature, but 30 degrees Celsius is going to be about 100 degrees Fahrenheit. So this is at a kind of warm temperature, is around 346. So we can see that the speed of sound is higher when our air temperature is warmer. Now, that is not actually due to density. That is due to the fact that our particles are going to be moving faster at higher temperatures. So if they're moving faster already, those collisions are going to be able to happen at a faster rate. Now, in solids and liquids, okay, these are much higher density mediums. So we can see in terms of density, gases, which are low density, are overall going to have a lower speed. Our higher density materials are going to have a faster speed. And that's because if our molecules are all closer together, they're denser together, then they are going to be able to bounce off of each other and collide and transmit that sound faster. So if you are listening to someone talk and you're sitting there in a pool and you decide to dunk your head underwater, it goes all wah, 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 wah. The sound gets all weird and funny. And that's because we're used to hearing sound in air, and our brain is used to interpreting those wavelength and speeds as sound. But we go down into the water, our speed of sound changes. Remember that our frequency is going to stay the same as we transmit into different mediums, but the wavelength is going to change, and so we're going to hear that wave differently. And so we don't hear as well underwater as we do in the air, because our brains are used to interpreting the sound in air. So we can see that water at 25 degrees Celsius has a speed of 1490 meters per second, whereas air at that same temperature is only 346 meters per second. Now, in general, higher density is going to give us faster speed. And like I said, in our gases, temperature is also going to make a difference. Now, the equations that I'm going to show you on the next slide are going to look kind of similar to this. We talked about the wave speed for waves that are traveling on springs. So if I had a string here and I was to send a wave along it, and that wave was going to propagate, it would be dependent on the tension and mu. Remember, mu was our linear mass density, mass per unit length. So this was basically a density factor. And basically the tension had to do with like how easily transmitted those are. So that's going to be kind of one of those factors. It's the restoring force. It's basically how much is my material kind of pulling back, trying to get my particles to go back to where they are. So when we look at our other materials here with our speed of sound, we have some different equations. And like I said, these aren't on your formula sheet either. They have just the very general kind of formula on there, just to kind of give you an idea for like the concepts. So on the numerator, we have kind of the bulk modulus. If we have a fluid, Young's modulus is kind of the equivalent for a solid. And so those are experimental quantities. And then we can see that density is on the denominator for both the fluid and the solid. Now, our ideal gases are going to have slightly different kind of relationships. So the molar mass on the bottom is going to kind of represent our density factor, kind of like inertia. It's basically inertia on the bottom. The numerator here is going to have our temperature factor. So we can see that when our temperature of our gas increases, our speed increases. And we saw that with our air, that our air that was warmer was able to move faster. Now, when we look at helium at 0 degrees Celsius compared to air at 0 degrees Celsius, helium has a very, very, very low molar mass. So if I have a very, very low molar mass, then that's also going to give me a very, very high speed. So our speed of sound in helium is going to be a lot faster. And so we notice that like with, if you've ever like had a helium balloon, you've like sucked it in, it goes, it sounds really, really, really high and squeaky. Well, it sounds really, really high and squeaky because the speed of the air through that helium as it's vibrating is going to change the way that the wave propagates traveling through that helium. And it's going to produce a sound that when your vocal cords produce that same vibration in air is going to create a normal sound, whereas when it makes that sound in helium, it's going to produce a much higher frequency, higher pitch sound. So we can kind of see how these three equations are really similar over here to our wave speed on a string. And then that numerator, like I said, that's kind of related to our restoring force. It's related to the motions and forces internally within our materials that are holding our particles in place and attracting them together. The more those molecules are held together, being pulled in on each other, interacting with each other on an atomic scale, molecular scale, then the higher the speed we're going to get. Now, there is a lot of different medical applications to sound. Ultrasound is now being used, of course, for imaging. It's also being used to break up tumors. They send sounds at tumors, and the sounds vibrate the molecules, help to break apart the bonds and break apart the tumors, which is really cool. So this is a 3D image of a baby that is created by ultrasound. So this is a higher resolution image than what you're used to seeing from an ultrasound. And it's created by taking a whole bunch of those two-dimensional ultrasound slices. Like if you think about what you picture, like here's your like little baby here. I can't draw anything, so don't do it. There's my little hands for my baby. Okay, and basically there's kind of the basic ultrasound. Now if you take a whole bunch of those and you stack them on top of each other, that's kind of what you get here with the 3D imaging. Now, why do we get this image? How can we see this detail inside of the human body? How does that work? Well, there's a lot of physics in it, and so if you're, you can just go on looking like what's the physics of an ultrasound to get more details. But basically, the way it works is that the little device probe sends out a sound that is at a known frequency, and that sound interacts with the tissues inside of the body. And because different tissues have different densities, the wave is going to travel at different speeds through there. It's going to bend differently. It's going to reflect, refract, and do kind of different things. And so that wave then makes it back to the sensor, and then the computer then interprets the wave signals that comes back and produces kind of this scan where darker areas and lighter areas, kind of like an X-ray, represent different tissues. And so we can kind of see that if we just look at the tissues here in the human body, that the speed of sound is going to be really, really high in bone. So like the skull bone is 4080. So that is going to produce a very big, more of a reflection because it's so dense. Some of that wave is going to get bounced backwards. And we can see that in our soft tissues, we're going to have slower speeds. And that is going to cause kind of the ability to be able to see these different features on whatever it is that the doctors are looking for. So now the intensity of the sound is related to kind of like loudness. How loud is the sound? You all know loud people. I'm a loud person. We make very intense sounds. So the intensity of the sound is related to power. Power is the power is the rate, missed that, at which energy is transmitted by the source. So we've got little birds here. So we got a little bird that's just kind of chirping around. So that's going to be a very low power wave. So it's producing pressure vibration. So once again, as the bird, it sounds like they're making a single sound, chirp, but they're not. They're actually creating a vibration that has a sinusoidal variation in pressure. Now, if that bird is unhappy and it's screeching at the top of its voice, that's going to be a higher power wave. Now, in the denominator for intensity is going to be area, because what happens is if I stand here and I listen to a sound that's coming from here, that sound has to travel out. And if I'm standing here that's further away, then what happens is that energy is being spread out over a larger area. So the area at which that sound wave has been able to spread is going to affect the intensity. So that the further away you are, the quieter the sound is. And that just kind of makes sense. We're used to that. So if we assume that we have a point source, so if our sound source is a point in space that is like infinitely far away from everything else, and there's nothing else around to interfere, then we can picture that that sound wave creates spherical, it's like a spherical bubble of sound that spreads out and grows. Because if I'm further away, that sound can be heard here and here and here and here. And so all these different parts, 360 degrees all the way around the surface area of the sphere, can hear it. So what happens is you take that intensity at a particular location and it gets spread out. That energy is spread out. So instead of just covering this area here, maybe it's spread out to cover a larger area. Well, in order for it to do that, the intensity has had to decrease. So for a spherically propagating point source sound intensity, we are going to assume that the area is going to be the surface area of that sphere. So our intensity is going to be our power over 4 pi r squared, okay, because that is the surface area of a sphere. Power is measured in watts. Radius would be in meters, so the unit of intensity is the watt per meter squared. If I were to create a graph of this, by the way, I kind of wish I should have stuck this in here, but if I was to create a graph of intensity, this is an inverse square relationship. So that means that if I was to create a graph of intensity versus radius, it would be a decreasing curve. And so these inverse square relationships mean that our intensity is going to decrease very rapidly with distance. We saw this with the gravitational force. The gravitational force is an inverse square. So basically, if someone is right up in your face and they are yelling at you, that is very, very, very loud. But if I was to double the distance, so if I was standing here in an R and I was hearing an intensity of the sound here, and I end up going at a distance of 2r, because it's an inverse square, I don't just hear half the sound, I hear 1/4 of the sound. So sound decreases pretty rapidly with distance. Here's an example problem. So the intensity of sound from a point source is 1.0 times 10 to the negative 8th watts per meter squared at a distance of 5.0 meters from the source. What will be the intensity of the sound at a distance of 25 meters from the source? So you could set up some proportions with this because we are assuming that our point source has constant power. The power we're using this, and I'm going to assume that I have the spherical propagating wave here. The power is the same because this is due to the source. So if I were to kind of solve this, I get that I times 4 pi r squared is equal to the power of the source. So that means that I at my original position and r at my original position is equal to the power of the source. But this also means that my power of the source must also equal my new position and the intensity. So what I can do is I can set those equal to each other. So I have I1 times 4 pi r1 squared is equal to I2 times 4 pi r2 squared. And I can see that on both sides the 4 pi's are going to cancel. And that gives me that I1 times R1 squared is equal to I2 times R2 squared. I am looking for the intensity of sound at the new distance. So I'm going to divide both sides by R2 squared. So my new intensity is going to be my original intensity times R1 squared over R2 squared. If you wanted, you could also have used the original information over here with our I1 and R1. We could have just found the power of the source. That's okay. I'm just skipping the middleman here so I have less rounding. So my I1 is 1.0 times 10 to the negative 8 watts per meter squared. My R1 is 5.0 meters, and that is squared, divided by my R2, which is 25 meters squared. And when you do that in the calculator, you get that I2 is equal to 4 times 10 to the negative 10th, and that would be watts per meter squared. So we want to compare that to our 1.0 times 10 to the negative 8th. So if I were to convert this guy here to 10 to the negative 10th, I would move the decimal to the right 2 times. So this is 100 times 10 to the negative 10th watts per meter squared. And my new one is 4 times 10 to the negative 10th watts per meter squared. So I can see that my original sound was about 25 times larger. And I could have answered this question without doing all the math if I had used proportional reasoning. So because my intensity here is proportional to 1 over r squared, I'm going from 5 meters to 25 meters. So my r is 5 times what it was. Because of the square, that means that I'm going to get 1 over 5 squared times, so approximately 1 over 25. So my intensity would have to decrease by a factor of 1 over 25. So if I take my original value divided by 25, that also would have given me the same answer. So there are different ways to go about solving this problem. One way I could have actually calculated power and then plugged into this equation again and then solved for the new intensity. Here I skipped the middleman and set those two kind of equations equal to each other. You could also have used proportional reasoning. Now, as you can see, that intensity was like times 10 to the negative 8 times 10 to the negative 10. Those are really, really small values. And the actual intensities that we can hear are actually really huge, and there's a lot of scientific notation involved. And so what they decided to do is, when we're going to talk about sounds, especially if you're like a sound technician, you don't want to be sitting there dealing with these times 10 to the negative whatever values when you're sitting here and trying to work with a rock band as they record a record or something. So instead they came up with what we call the decibel scale. It is a logarithmic scale that is used to kind of simplify and kind of compress the intensity levels into a smaller range of kind of more normal looking numbers. So if we wanted to calculate the sound intensity in terms of decibels, we use beta, the Greek letter capital beta here to, actually it's lowercase beta, sorry, to represent sound intensity, so instead of I. And then we take the logarithm over here of the intensity of the sound wave, that would be in watts per meter squared, and then we are comparing that to a reference intensity. And that reference intensity is set and fixed at 10 to the negative 12 watts per meter squared. So I0 is always equal to 10 to the negative 12 watts per meter squared on the scale. So if I take some other wave, I take the ratio of the intensity of my new sound to this reference level I0, and I then take the log base 10 of that, not the natural log base 10, and then we multiply it by 10. Now, log base 10, when you calculate the log of 1, that gives you 0. So if the intensity of my sound wave is equal to I0, then that would be an intensity of 0, and you basically wouldn't be able to hear that sound. Okay, there'd be no intensity. And then we would multiply that by 10. 0 times 10 is still 0, so our decibel level would be 0. So whenever our intensity sound wave is equal to 10 to the negative 12th, our reference intensity, that decibel level is 0. The larger and larger the intensity is, the bigger we are going to get for that decibel scale. So here are some example values. So our threshold level, okay, that was selected at 10 to the negative 12th watts per meter squared. If we have a 1,000 hertz sound, that is what the intensity would have to be for us to hear it. So if you notice, when you go back to our demonstration at the start, I had to keep changing the volume. Those lower frequency sounds were not very intense. They were harder to hear. So in order to possibly be able to hear them, I had to increase the volume level of the sound being produced. And I had to increase the intensity, the power output. You then also had to hear it, and you think about that intensity was being transmitted. It had to be picked up by my microphone, and it then had to be transmitted into your speaker. So depending on what that distance is, that also affects the intensity. So there's a lot of things that affect the actual baseline intensity, but that is what the 10 to the negative 12th watts per meter squared was set to be. We set 0 decibels. So you can actually have a much narrower scale. So we look here. So a military jet aircraft at 30 meters away. That's not very far away. So picture you're in an air show, you're watching Top Gun, you're standing there on the deck of the aircraft carrier, and that jet flies by you. Man, that is going to hurt your ears, and that is going to be an intensity of 10 squared, which is about 100 watts per meter squared. So 100 watts per meter squared is a huge intensity of sound, and that corresponds to 140 decibels. So a whisper is about 20 decibels. The threshold of pain here is at 120 decibels. So think about your rock concert, your ears are starting to hurt, types of things is where you're going to get kind of that damage range. Basically anything kind of in this range or above could possibly cause damage to your hearing. That's why you're not supposed to listen to your earbuds really loud in your ear and blare the radio in your car. Yes, Mom, I know. But seriously, it can damage your ears, and it can increase this threshold. So when you get hearing damage, basically your minimum threshold to hear actually can increase over time. Other things like scar damage, nerve damage can also cause changes to your ability to hear certain sounds and that minimum threshold that it takes to hear a sound. Now, a good estimate for understanding kind of how the decibel scale relates to kind of intensity is a 3 decibel increase is double the intensity of the sound. So if you just go 3 decibels higher, you're doubling the intensity. If you go 6 decibels higher, that is going to be 4 times the intensity, on and so forth. So that is going to be a really, really big kind of difference. So small changes in the decibel scale create huge changes in the actual intensity because of the behavior of that logarithmic function. So here's an example problem. We have sound emanating from a particular source, travels in all directions. This sound is measured at 20 decibels by an observer standing 40 meters away. In order to decrease the intensity level to 10 decibels, approximately how far from the source must the observer be? So this is going to require us to kind of combine what we talked about with intensity and power and now the decibel scale. So if we think about what's going on here, so we're going to have kind of this kind of starting location. So you're still going to have your source, and we're still going to assume that our source is going to be creating these spherical waves away. So we are starting here at some particular distance value that is going to be 40 meters away. And at 40 meters away, we have a decibel level here at the start that is 20 decibels. And we want to know how far away do I have to be? So what is my new value of R? So what's R2 if I want my decibel level to now be 10 decibels? So we have that our decibel scale is 10 decibels times the log base 10 of I over I0. So what I can do here is I could solve for the intensity of the wave. That is one thing that I could do. That might be, we can use this original value to do that. So I would divide both sides by the 10 decibels. So I get beta here over 10 is log of I over I0. And then to get rid of the log base 10, you raise both sides to the power, 10 to the power of. So we get that 10 raised to the power of beta over 10 is equal to I over I0. So then to find the intensity of that wave, I'd multiply both sides by I0. So we get that I is going to be I0 times 10 to the beta over 10. So one way we could solve this problem is we could actually calculate I and find out what that intensity actually is. We can then, once we have that intensity, we can go back and plug it in to our power equation. So with this, with our known value of our decibels, let's see, we can figure out what our intensity was originally. So we can do that here. We'll find I1. So if I'm finding I1, that is going to be our I0, that's our 10 to the negative 12, times 10. Our decibel level is 20 divided by 10. So with this, in the power here, we have 20 divided by 10, which is just 2. 10 to the power of 2 is just 100. If you multiply 10 to the negative 12 times 10 squared, that gives you an intensity of 10 to the negative 10th watts per meter squared. So I don't really have to do that in the calculator, but I could if I want. So we found I1 is going to be 10 to the negative 10th watts per meter squared. Now we can do the same thing, and we can actually find our value for I2. So I2 is going to be 10 to the negative 12. 10, and now this time we are 10 divided by 10. So this one is going to be the 10 cancel to 1, so just multiply by 10. So I2 is just 10 to the negative 11th watts per meter squared. So that's what we need with that equation. Now we have to go back and think about what we did with our spherical power source. So I'm going to clear this up a little bit. Now I know we did this derivation just a couple of slides ago, but just as a refresher, our intensity of our wave is power over 4 pi r squared when we're talking about a spherical wave, and we're going to assume that that's true. So what we did is we solved for power, because power is going to be the same for both of these waves. So I get I'm going to just do 4 pi r squared times I. Actually, here, hold on, let me rewrite that just a sec. So I'm going to do 4 pi r1 squared I1 is going to have to equal 4 pi r2 squared I2, because we multiply by 4 pi r squared on both sides. So the 4 pi's cancel, So we had that R1 squared I1 is equal to R2 squared I2. We are looking for R2, so we would divide both sides by I2 this time. So a little bit different than the one we did before. So we get that R2 squared is equal to R1 squared I1 over I2. And then we can take the square root on both sides. And I can write that, I can take the R1 squared out and just make that R2 is R1 times the square root of I1 over I2. And then I can just plug in my values. R1 was 40 meters away. And then I1 was R10 to the negative 10 watts per meter squared. Our I2 is 10 to the negative 11 watts per meter squared. You could, of course, plug it in the calculator right here, but just to simplify, to kind of see what's going on, if you simplify the scientific notation, the negative 10 and then 10 to the negative 11th there, that just reduces to 10. Because you end up with 10 to the negative 1, 10 on the bottom, 10 to the negative 1 on the bottom. So that just ends up being 10. You're basically, the numerator is 10 times higher than the denominator. Sorry, easier way. So if you take 40 times the square root of 10, we get that you would have to be approximately 126 meters away. So that's approximately 3 times the distance. So we would have to about 3 times the distance in order to get our decibel levels to go down by half. So now we're talking a little bit more about kind of how do we perceive sound. So we have intensity as one way. The other way we hear sound is kind of with frequency. So as we saw at the beginning, we did the demonstration, lower frequency sounds have a lower pitch, higher frequency sounds have a higher pitch. So whenever we are talking about wavelengths and frequencies, we have to remember that our wave speed is going to be constant in our medium. So as long as we're staying in air and we're staying at the same temperature, our wave speed is constant. And that there is going to be that inverse relationship between frequency and wavelength. So that if we have a shorter wavelength, that is going to correspond to a higher frequency. So when you look at a wave, well, that wave didn't turn out very well. Let's try that one again. There we go. So this wave has the wavelength that is shorter. The wavelength on this one is longer. So what ends up happening is that our frequency on this is a higher frequency wave, and this is, of course, a lower frequency wave. So that is kind of the first thing, just to kind of refresh our brains on the relationship between wavelength and frequency. That's going to come to play here in a little bit. And then what we think of as hearing a single sound is often not a single sound. It's actually the superposition, so the combination of a whole bunch of sounds at different frequencies. For example, if you were to play a sound on a musical instrument into a microphone and have sound software analyze it, what ends up happening is it gives you this pressure wave. So this pressure wave here, we have different pressures. There's some peaks. There's some like smaller peaks embedded within the larger peaks. So we could then calculate the frequencies and periods. And what they do is they essentially pull out the different flavors, essentially, of the wave that are inside of here. So I could just kind of look at this wave and I could see that there's some like overarching patterns. Like I can see there's like a peak here and a peak here. And that is kind of driving this overall pattern. So there's kind of a large kind of scale like wave kind of going on here like this. So we have this kind of overarching kind of wave that's happening here. But then we've got these smaller frequency waves, and there's kind of embedded on top of this, there's probably some sort of smaller frequency wave that is being added. There's kind of a medium frequency wave that I can kind of see here. So it's kind of like this, like medium frequency that's kind of coming in. I'm not doing this very well because I'm not a computer that is pulling this out and analyzing it. But I can see that there's a bunch of different patterns here. There's some longer term patterns. There's some short scale patterns. And if you take the computer and the computer does an analysis and it basically filters the sound wave for different frequencies, which is essentially what sound technicians do when they're processing, a studio recording and they're cleaning up and making it sound better. They run it through a bunch of filters and they take, there's this high squealing sound that's in the background. Let's filter that out. Let's take that wave, that high frequency out. Or I want to hear more low frequency or higher frequency. They can pull out these different frequencies and either emphasize them or remove them entirely. So how they do that is they can actually produce a chart that gives us the amplitude, so the actual amplitude of each of these waves. So the little green wave might be a low amplitude wave at whatever frequency that is. The one I drew blue was that was a higher amplitude wave. And that's what we're kind of seeing here. And notice me pulling the word harmonic back out here. We saw harmonics when we talked about waves on a string. So what happens is each of these different frequencies, like my little green frequency wave might be this peak right here. My little orange one might be this one here kind of in the middle. And then that blue one, that wave that I drew might be this peak right here. And so this is the amplitude for that wave. And what they found is that for instruments in particular is the peaks all end up being multiples of some fundamental. So we've talked about the fundamental frequency. And if we kind of break down kind of this little diagram right here, so we have 5, 4, 3, 2, 1. This peak right here represents the fundamental frequency. And then there's actually not really anything here at the second harmonic. So if I double the frequency, that would be my second harmonic. And then my third harmonic here. And then my fourth harmonic doesn't really have much. Then my fifth harmonic. So I have harmonics, but they're not all the same amplitude. And I can see that sometimes some of my really high frequency harmonics can sometimes be at higher amplitudes than some of my middle ones here. And the way that these amplitudes and those frequencies come together is what we hear as sound. It's what makes the difference between a clarinet and an oboe and a trumpet and a saxophone and a whatever else that you're doing. And is kind of how these frequencies overlay themselves. So what we have to do is we kind of have to look at this concept of superposition, which is the addition of waves. And then we're also going to eventually look at harmonics. But we're going to look at interference and how the waves interact with each other. And then kind of end with returning to our waves on a string and looking at how do waves in air, how do sound waves in air kind of work similar to that. So the first one here we have is the beat frequency. So when we have two waves that overlap, if they are very, very similar in frequency but not quite identical, then you can actually hear kind of a pulsing of the amplitude. Musicians actually use this to tune their instruments, because if one flute is sitting next to another flute and they're supposed to be playing the same frequency, but one's a little flat or sharp, which means their frequencies are a little off, then they can hear kind of this wave vibration. And I'm going to do a demonstration here for that. But you can see that these two waves right here are just a little bit off. And sometimes their waves are really similar and they're going to get a maximum. And sometimes they're exactly opposite of each other and they're going to kind of get these minimums here. And there is an overarching kind of pattern here that you can see. And if this is the amplitude, at some points, that wave is going to get very, very quiet, and at other points, it's going to get loud. So we're going to listen to this. I'm going to open this tone generator up again, and this time I'm going to try and open it up twice and see if I can make this work. All right, so what I'm going to do here is I have two of these windows open. 440 hertz it's going to be a standard tuning note actually for orchestras. So I'm just going to pick this tone to start with, and I'm just going to play it on one speaker here, or one source. Okay, so we can hear that tone. And I'm going to come over here to the other one and play that same tone. So right now you should probably be hearing just one tone. But what I'm going to do is I'm going to change the frequency just a little bit. Actually how instrumentalists in a band or an orchestra, how they actually tune is they listen to each other and they play the same note. And if they don't have like a tuner in front of them that tells them whether they're sharp or flat, they listen and they try and adjust their pitch until those beats go away, until you can't hear the beats anymore. So basically, as those waves add up in constructive and destructive interference, where you get pure constructive interference is going to be the maximums, and where you get destructive interference is going to be the minimums, and you're going to get this oscillation in between. To calculate the beat frequency, it's just the absolute value of the difference between the frequencies. So the closer the frequencies are together, the slower the oscillation. So that's where you got the wah, wah, wah. If they're the exact same frequency, you only hear just a single tone. But the further they're off, the more vibrations you get. Wah, 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 wah. So that's how the beat frequency works. Really key for musicians. So another thing that can happen is instead of having those playing that same frequency at the exact same location, the further apart you are producing those frequencies, we can also get other types of interference. So different from a beat frequency. So if you've ever had to set up a surround sound system, one of the things they give you a microphone that you have to connect, and you have to move it to different locations in front of the different speakers. They tell you to put it here, and it makes these clicks and it makes these sounds, and it analyzes it, and it might tell you, oh, you need to move this a little further left, a little further right, or they'll tell you, the computer itself inside of your sound system will adjust, and it's basically trying to figure out where are you sitting so that when you're in the center of your surround sound, you're getting the best sound possible, the best construction of all of the waves in your room. Because there's going to be echoes, there's going to be reflections off of the walls, and that's kind of what that's looking for. Now, on a simpler scale, if we take two speakers that are playing the exact same sound, what's kind of crazy is if you stay at like a particular distance from the speakers, as you walk, what you're going to hear is you're also going to hear kind of an increase in amplitude and a decrease in amplitude. Kind of like the beats, but it's not going to be an oscillation. It's just as you walk, like this location right here, it might be really, really quiet. And then as I walk here, it might be really, really loud. And as I get here, it might be really, really quiet. And then really, really loud. And then really, really quiet. all staying about the same distance from it. So this is two source interference. So here is a demonstration. If you don't know what I'm talking about, we're going to watch a quick little video. So there's the two speakers, and there's the sound. The camera is going to move, simulating walking. Quiet, loud, quiet, loud. So you can see that there's this pattern. You're staying the approximate same distance. We're not walking towards or away. You're just walking sideways. So you're seeing these patterns of constructive and destructive interference. So how does this work? So what happens is at the different points that you're at, these waves, if we picture these waves, we picture them as wave fronts. So like the crest, so the crest of these kind of dark solid lines right here. So each one of these crests represents that positive maximum amplitude. And then the white areas in between, those are representing the troughs. So we've got our crests and we've got our troughs. So these different points are different labeled. So the blue points represent where a crest and a crest intersect. So that is pure constructive interference. So that's going to happen when those two waves hit at the exact same instant, crest and crest, identical sound sources, same frequencies. They're going to be crest, crest, they're going to add up. That's going to be a maximum of sound. The little red dots here, that's purely constructive, but it's two troughs. So that is also going to add up to be a maximum, okay? Because all that means is it's negative at that point, the next moment it's going to be positive. Now, destructive is going to happen whenever a crest and a trough interact. So whenever you get kind of the white representing our trough and then the solid, when those interact, that's going to be your pure destructive interference. So that's going to be this option down here, like at C, where you have a crest and a trough line up. Those two waves are going to add up and cancel each other out. So what's going to happen with that is that's going to be your quiet point. So as you walk, keeping kind of the same distance from the center of those speakers, you're going to end up going through a destructive, a constructive, a destructive, a constructive, destructive, constructive, along that. So you're going to hear that change in frequency. Well, they like to sometimes have you do calculations for this to figure out, well, what is the wavelength of the wave, or what was the frequency of the wave, or where would you need to stand in order to hear a quiet spot? Where would you stand if you needed to hear a loud spot? So this is kind of the process. The idea is that you've got a path difference. So if you look kind of at the geometry of the wave, so if I'm starting here like at source 2 and I'm standing here at point 2, this wave here that is coming from here is having to travel a certain distance. Okay, that distance is here. Now, the speakers are a certain distance away as well. So this is creating a difference in the amount of distance that it has to travel. So from this first source, from source 1 over here, that is going to be a much larger distance. So there's actually a triangle here that is being made. And if you could kind of picture what's going on, you could make a right triangle. It's actually an isosceles triangle. Sorry, not a right triangle. It's an isosceles triangle. If you make an isosceles triangle so that these two sides are the same, then they have the same path length. The difference here between those two paths, where those lengths are, that's what we call delta R. That is our path difference. So that path difference is what is causing the possibility for destructive and constructive interference. So if I look and I kind of count like the wave here, I have 1, 2, 3, 4, 5, 6 wave crests, and then I'm ending up kind of with this trough coming into this point. When I look at the wave that's coming here, it's also coming in at a trough. So whatever the difference in the waves is here, there is a full wavelength difference in that, so that I'm still getting a trough and a trough coming into that point. So that's actually going to end up with constructive interference. Trough, trough, crest, crest, either way. Now, when I look at point 2 over here, point 2 is a little bit different, because I can see that when this wave comes here, I have this crest coming out over here, whereas from source 1, I have a trough coming in. So at that point, I am going to be having destructive interference. So if I was to find whatever the path difference is here, if I was to actually create that, and this is my isosceles here, that's the isosceles here, so those are the same. So I would still have my path difference would be delta R, it's the difference in those, and there's a triangle there, lots of triangles in this. What's going to end up happening is that path difference is not going to be based on a full wavelength. So our path difference R for constructive interference is going to be some multiple of a whole wavelength. So that no matter which path it takes, I'm always going to get the same part of the wave, either a crest and a crest or a trough and a trough, coming together and passing through that point, so that they're always going to add up. With destructive interference, you have to have half of a wavelength between them. So you're going to have some multiple of n plus a half times that wavelength, because one of them has to cancel out the other. So there's going to be a half a wavelength shift. Now, n could be any integer, because there could be lots of multiples. The simplest form of this, it would be just like if I have a right triangle here, they're a little bit easier problems to solve. And if I think about one single wavelength here, if my wavelength is such that the distance that I'm standing at this position right here is one full wavelength, if I have a distance here that is exactly like half a wavelength off, then I can see that this is my wavelength here, this is my wavelength here. My delta R, the difference there, because I could do just delta R is like length 1 and length 2. It's going to be basically the absolute value of length 2 minus length 1. In this case, it's going to just be half of a wavelength. But if I double the frequency of that wave, I might go through 2 full oscillations, in which means I might go through 2.5 oscillations here. So I could have an even faster wave, but I could go 3 oscillations here and then 3.5 oscillations. So the whole point is just you need to have some sort of multiple of a half to have destructive interference, and you should have integer multiples of R, delta R, in order to be able to find those values. So we can look here at this example problem. So we have 2 source interference. We have 2 speakers that are 9 meters apart. They emit identical sound waves. So we can assume that they have the exact same frequency. They're traveling at the same speed. And we've got a person that is standing here at point X, and they're standing directly in front of speaker 1, and they hear a minimum in the sound amplitude. So this tells us that we have destructive interference at this point. So I can make a right triangle out of this. So I have the fact that my delta R here is going to be some distance that gives me basically 12 meters here and 12 meters here. And my delta R is right there. Now, this is really nice that it's a right triangle, because that means I can use the Pythagorean theorem to represent the distance d here between them. I can call this one like the length L here for that, and I can do the fact that my hypotenuse here is going to be the square root of L squared plus B squared. So I can find that hypotenuse, and I can use that hypotenuse to find delta R, because my hypotenuse is going to be delta R plus 12 meters. So my delta R is going to be my hypotenuse minus 12. So if I do that, I'm going to do 12 squared plus 9 squared, which is just going to be 15 meters. So my delta R is going to be 15 meters minus 12 meters. So my delta R here is 3 meters. Now, because I want destructive interference, I know that my delta R has to be n plus a half times my wavelength of my wave. Now, what I'm going to do is I'm going to assume that there's lots of different waves that could have done that, but I'm just going to choose the wave that gives me n equals 1. But I could come up with lots of different wavelengths that match this. But I could set n equal 1, I could set n equals 0. Actually, I'm going to do the simplest one, actually, is we set n equals 0. That's going to be when we are only half a wave off. So we're going to have that our delta R is just going to be 1/2 times the wavelength. So our wavelength is just going to be 2 times delta R. So 2 times 3 meters. So this is going to be a 6 meter wavelength wave. And if we say wanted to know like what frequency wave that would do that, we can always use our wave speed is equal to wavelength times frequency. And our frequency is our wave speed over wavelength. If I wanted to find what frequency wave it is that would do that, then all I would have to do was plug in like the speed of sound. So this question can be tied into other questions related to like the speed of sound. But that gives me the fact that a 6 meter long wave, which would give me, let's see, speed of sound in air is about 340 meters per second. So if I divide that by 6 meters, what do we get? So that would give me about a frequency of about 56 hertz. That is a really, really low frequency. We said that like 20 hertz is like the lowest that human ears can hear. So is that the most likely wavelength of the wave if we can probably not really hear it? No. So it could also be that instead of n being 0, it's possible that n could be 1. Well, if n is 1, then how does that change my math? Well, if it changes my math, because instead of using 1/2 times wavelength, I would use 1.5, so I'd use basically 3/2 times the wavelength. So when I multiply and get wavelength by itself, instead of having double, I'd have 2/3. So 2/3 of the wavelength would give me a 2 meter wave. So then if you plug in 2 meters, then you're going to get a wave that is 3 times larger. So then you'll have a higher frequency wave. So you're going to have kind of the possibility for multiple different waves, multiple different frequency sounds can be emitted from that speaker and still hear a minimum right here. Now, if I was hearing a maximum, then you would do the same process, but if you were hearing a maximum, instead of being destructive, you would do constructive. And instead of using the n plus 1/2, you would use the delta R is equal to n times the wavelength. So very, very similar processes. A little bit of geometry and kind of understanding kind of the relationship between the path length. All right, so our last topic now is standing sound waves. So we talked about standing waves on a string. The idea if I can send like a wave pulse along the string, and then that wave pulse can propagate along. But if there's a boundary, then that wave pulse can end up bouncing back, and then that wave pulse can can travel, and those waves can then interfere with each other. And then they can create these standing waves where you've got perfectly spaced waves, and you get kind of this vibration that occurs. And that's kind of how like guitar strings and stuff like that work. So similar things happens in pipes, except for instead of a string vibrating and actually creating the physical shape here of the standing wave, it's really a pressure wave where you have low pressure and then you have higher pressure. But as you do the same, instead of this high pressure doesn't move. This high pressure stays in place. And these high pressure areas vibrate, these low pressure areas vibrate, high pressure vibrates, but the wave itself doesn't travel. These spots always stay high pressure, these spots always stay low pressure. So to kind of visualize this, because it's harder to see than a string, they invented these kind of fire tubes. They're called Rubens tubes. And they use fire to show the standing waves. So I'm going to show a quick little demonstration of that here. So you can see that some of the frequencies produce these very, very nice patterns of high frequency motions. Not every sound, not every frequency. Not every frequency can produce this nice, perfect wave that you see kind of here on the screen. Because in order to produce a standing wave in a pipe, you have to have that wave have a wavelength that matches the length of the pipe. So for example, we've got like a high pressure here, and then a low pressure, and then a high pressure, and then a low pressure. For example, if our pipe's open on both ends, we actually have to have kind of a node or an antinode on either end. So you can't just have any wibbly wobbly sort of wave. So with our wind instruments are actually making all of these different frequencies. So we talked kind of about like the overlaps here, and the idea that you have different amplitudes of different waves, and that you can pull out these frequencies, and that you can have like your fundamental frequency here would be the first one, and then we've got like, that would be around 145 hertz. So double that, there should be another peak. There's not a peak here, but there is a peak here. So there is going to be some sort of overlap that's created. This is actually a clarinet, and a clarinet is modeled as a pipe that is closed on one end, on open on the other, because the mouthpiece of a clarinet creates kind of this closed end. They vibrate a reed, and then you've got the bell over here that is open. And so the fact that it's closed on one end means that it behaves a little differently than like if you picture like a pipe that was open on both ends. A flute actually is modeled as that, because even though it's kind of closed on one end, you blow across this open hole, and so you are actually creating vibrations that from an open end to an open end, even though it's not open technically on both ends. So you've got these different patterns, and then how these patterns overlap creates different frequencies. Oboes have very interesting harmonics. Clarinets are a little bit more regular. Flutes are even more regular. So it's going to be based on kind of the shape, the fact that, you know, like oboes and clarinets are made by vibrating reeds where you're blowing over a hole here. Trumpets and brass, you're buzzing basically a mouthpiece. So all of that is doing in creating kind of these different wave patterns. So when you break apart the different kind of instruments and looking at those graphs of their frequencies, the lowest frequency on any of the graphs that is played is always going to be your fundamental frequency. So whatever that lowest frequency that's picked up is going to be your fundamental. So these are actually just showing harmonic numbers, so that's going to be your first harmonic. And then all of your other frequencies should be multiples of that fundamental. But different instruments have kind of different dominant frequencies. So the flute usually has the highest amplitude being the first, the fundamental, okay, your first harmonic, and the second one's lower, and then third and fourth and so forth. Those get lower and lower and lower kind of over as you go. The clarinet, it's the odd numbers that create high amplitude waves, and the clarinet's not a perfect closed pipe. If a clarinet was a perfect closed pipe and it was just a tube that was closed on one end, then there would actually be nothing from the even numbers. And I'll talk about why that in a second. The oboe is really interesting and has very interesting sounds because actually its fundamental is not the loudest amplitude. Actually, it's kind of some of these middle amplitude ones that actually have higher, and that's part of what gives the oboe kind of its very interesting mysteriousness with it. You can see that the trumpet's kind of a combination. It's got a little bit more where the, kind of like the oboe, where the fundamental was not the loudest. But it looks like, for the most part, most of the frequencies are kind of creating a decreasing amplitude. There's a few little oddities there. So we can model these instruments as like a simple like open pipe versus a closed pipe. Your open pipe has to be open on both ends, and it's going to have a fixed length. And in order for a wave to produce a loud amplitude sound in a perfect ideal world, you'd have to have a perfect antinode perfectly fit. So not every frequency is going to have a wavelength that is going to match the length of this tube. Kind of like when we did the strings, the wavelength of the string didn't match the length of the actual string itself. Now, the closed pipes, you actually have to have a node on the closed end and an antinode on the open end. So when we look at the open pipes, all our equations we did for harmonics kind of still work. So the fact that your harmonic frequencies are always multiples of the fundamental. Now, we're using wave speed is wavelength times frequency, but we've solved for frequency. Frequency is going to be wave speed over wavelength. Now, at a minimum, in order to produce an antinode in each end, the lowest wavelength wave that'll do that is going to be this guy right here. And if you picture, that wave actually continues up on. That is going to be a wavelength. That is going to be a wavelength that is exactly half. That's actually double the length of the tube. Sorry, double the length of the tube. The length of the tube is half of the wavelength. So that wavelength is always going to give you the fundamental. So if you know the length of your pipe, you can calculate what wavelength is going to give you that fundamental. So that's going to be our fundamental right here. Now, if I double the frequency, that means I'm going to go through one full wave. So this is one full wave right here in the length of the tube. So my wavelength is equal to the length of the tube. So I can do that, and I could calculate the frequencies for each of these and the wavelengths for each of them. But in general, our wavelength for our fundamental has to equal 2L. So our wavelength for a fundamental open pipe is equal to 2L. And then if I want to find any other frequency, I can just multiply there. I can also then plug in, and I can use this equation once I know frequency to find any other wavelength. So different ways to make it work. So the open pipes, your fundamental wavelength is 2 times L. And then, of course, all of your frequencies, every multiple is going to give us an antinode. So this is our second fundamental. If I do 3 times the halves, this is going to be 3 halves. This is 1 half. And then we're going to have the second half, and this is the third half. So that's 3 halves. So I have 3 times the waves, and so all of those are going to sound. Now, when you come and looked at the closed pipes, it's really weird. Only the odd harmonics are going to produce a sound. So at a minimum, our fundamental here, in order to have an antinode on one end and the node on the other, this right here is actually 1/4 of a wave. So if I picture a wavelength here, I'm cutting that off right here. So my standing wave is 1/4. I didn't quite make that fit right well. So this right here is 1/4 of a wave. here's another fourth, here's another fourth, here's another fourth. So that is my fundamental here. So on this one, my fundamental wavelength is 4 times the length because it's 1/4 of a wave is fitting inside that. Now this is the first harmonic. Now the second harmonic here is actually missing. Why is the second harmonic missing? Well, the second harmonic is missing because if I want to double the frequency, I need to have half of a wave. Well, when I do that, I get a node on the end. That's basically like pinching off your sound. You're not going to have any sound because there's basically no pressure propagating out because that represents a low pressure point. I mean a no pressure point. So this point right here is representing atmospheric pressure. So this is always at atmospheric pressure. So if it's always at atmospheric pressure, if I'm standing here and I'm trying to listen, then there's no difference between the atmospheric pressure here and the atmospheric pressure here. I'm not hearing a sound wave. This right here is going to be louder because I'm going to hear a sound because my pressure here is greater than my atmospheric pressure. I'm hearing a disturbance. And that wave is going to vibrate and that is going to create that loud. So I'm going to get that higher pressure sound on the end. So my second harmonic exists, but it doesn't produce a sound in a perfect closed pipe. Now, like my clarinet, I had a little tiny peak because there will be a little bit of a sound there. It kind of has a little bit of an overtone, but it's not a dominant harmonic. And then now I need to have 3 times that. So now I need to go through 3 halves. So 3 halves is going to bring me back over here to an antinode. So this is my third harmonic. Fourth harmonic doesn't sound because it would give me this full closed end. So that would be the fourth harmonic. So then I need to add another half on there to make this. This is my fifth harmonic. So for a closed pipe, you have to, our fundamental wavelength is 4 times L. And then you can still use that our frequency of all the other harmonics are N times the fundamental, but only the odd are going to sound. So comparing what we've learned so far about waves, standing waves on strings, closed pipes, open pipes. So we can see that there's a lot of similarities between the strings and the open pipes because all the harmonics will sound and the wavelength of the fundamental is 2 times the length of the string or the pipe. The difference is the strings have to have nodes on each end and the pipes have to have antinodes on each end. The closed pipes are different. They're closed on one end, open on the other. Their wavelength of their fundamental is 4 times L, and the odd do not, are the odd are the only ones that do create a sound. The even do not, because you cannot fit an antinode on the end for those frequencies. So here's an example problem. A sound is produced in a pipe that is open on both ends that has a frequency of 300 hertz and produces the standing wave shown. What is the fundamental frequency of the pipe? So a couple things we have to realize. This is open on both ends. And we have to figure out which harmonic this is. So we have to recognize that for our pipes that are open on both ends, we have to have an antinode on both ends. So that would actually be here. So we don't have the first harmonic. So I need to look what happens if I double that frequency. So that's what I end up having right here. So this is not the first harmonic. It is actually the second harmonic. And we can compare that to our diagram on the previous page. And you can see that that is what we have right here. That is our second harmonic. So now that we know that we have the second harmonic, this 300 hertz, that is the frequency of the second harmonic. We know that the frequency of the fundamental is, the frequency of the second harmonic is going to be 2 times the frequency of the fundamental. So if I want to find the fundamental frequency, then what I can do is I can just take my frequency here and divide by 2. So that's going to be 150 hertz. Now there's other things we could do with a problem like this. if we knew the speed of the sound, if this is air at room temperature, for example, we could assume that our wave speed is about 340 meters per second, and I could find the wavelength. So the wavelength of this wave, the current one that's being shown, if I use wave speed, is wavelength times frequency. Wavelength would be wave speed over frequency. So that would be about 340 meters per second divided by 150 hertz. That would give me a wavelength of about 2.3 meters. And when we look at this, we know that since we are dealing with an open on both ends, that our wavelength here would go all the way across. So this is actually showing one full wavelength. So my length here is going to be my wavelength. So I actually know that this pipe is 2.3 meters long. So it could actually give me the length of the pipe. Or if I knew the length of the pipe, I could find the wavelength and do something else. Or if I want to do something fun, I could put this pipe into helium, and I could use this experiment to calculate the frequency of the speed of sound in helium. Or I could actually use helium as the speed of sound and then do frequencies using that as well. So there are some additional tutorial videos here. One topic that we did not cover was the Doppler effect. It's really cool, but it's not part of our curriculum, so it was not something that we needed to explicitly cover here in our lecture video. But just in case it does, it's cool. And just in case it does come up, there's some concepts here with the Doppler effect in this video. Here is another two-speaker interference problem, more problems with harmonics, and some speed of sound using like the bulk modulus and some of those other equations kind of earlier on there for you. Well, I hope you learned something about sound and music, and hope you enjoyed this video. Good luck.